So, good afternoon everyone. Today I am going to discuss about the computer organization subject unit 2. So, in the previous class we have discussed some topics about the unit 2 section second section. So, I am going to continue the topics coming to the addressing modes. So, the way the operands are chosen during the program execution is dependent on the addressing modes on the instructions of the instruction. The operand is nothing but we are using some letters like A, B, C, D, this like operands, and we can use some values like 3 into 4 this like by using the operators middle of that operands. So, that is called the operands. The way the operands are chosen during the program execution is depend on the addressing modes of the instructions. The computer uses the addressing mode techniques. The computer using the addressing mode techniques. So, whatever the computer we are taking, that computer is using the addressing mode techniques for the purpose of accommodating one or both of the following provisions. So, we are giving the programming versatility to the users by providing the such facilities as pointers to memory, counters for loop control, indexing of data, and program reallocations. So, this is the first one, and second one is we are going to reduce the number of bits in the addressing field of the instructions. So, these are the two one or both of the following provisions we are taking in the computer. So, most addressing modes modify the address field. Most addressing nodes is modifying the address field of the instructions. There are two modes that need no address field at all. So, these implied or immediate modes. So, what is the address modes to say? The most of the addressing modes is modifying the address field of the instructions. There are two modes that need to know address field at all. Those fields are called implied and immediate modes. So, coming to the implied, what is meant by implied modes? So, now we have to know what is meant by implied modes. So, what is the use of implied modes? So, this is the implied modes. In these implied modes, operands are specified implicitly in the definition of the instructions. For example, the instruction complement accumulator is an implied mode instruction because the operand in the accumulator register is implied in the definition of the instructions. So, in this mode, the operands are specified implicitly in the definition of the instructions. So, we are taking the example like the instruction is complement accumulator is an implied mode instruction because the operand in the accumulator register is applied in the definition of the instruction. All the registers reference the instructions that use an accumulator are implied mode instructions. The zero address in a stack organization computer is implied mode instruction. This is called the implied mode. Next, immediate mode. What is meant by immediate mode? In this mode, the operand is specified in the instruction itself. The operation is specified in the instruction itself. In other words, an immediate mode instruction has an operand rather than an address field. So, whatever the operands we are specifying, that can be specified in itself in the instruction. In other words, we can say immediate mode instruction has an operand rather than an address field. So, the immediate mode instructions are useful for initializing the registers to a constant value. So, the address field of an instruction may specify either a memory word or a processor register. When the address specifies a processor register, the instruction is said to be a register mode. So, what is meant by register mode? So, the register mode is nothing but the mode. In this mode, the operands are in registers that reside within the CPU. The particular register is selected from a register field in the instruction. That is called the register mode. So, coming to the register indirect mode. What is meant by register indirect mode? In this mode, the instruction specifies a register in CPU whose content gives the address of the operand in the memory. So, in the other words, the selected register contains the address of the operand rather than the operand itself. The advantage of this register indirect mode instruction is that the address field of the instruction uses few bits to select a register than would have been required to specify a memory address directly. So, that is called the register indirect mode. Next, coming to auto increment or auto decrement mode. So, this is similar to register indirect mode except that the register is incremented or decremented after or before its value is used to access the memory. The address field of an instruction is used by the control unit in the CPU to obtain the operand from memory. Sometimes the values given in the address field is the address of the operand, but sometimes it is just an address from which the address of the operand is calculated. So, the basic two modes of the addressing used in CPU are direct and indirect address mode. So, what is meant by direct address mode and indirect address mode? So, coming to direct address mode. So, what is meant by direct address mode? So, in this mode, the effective address is equal to the address part of the instruction. The operand resides in memory and its addresses is given to directly to the address field of the instruction. In the branch type instruction, the address field specifies the actual branch address. So, this is called the direct addressing mode. Coming to indirect addressing mode, in this mode, the address field of the instruction gives the address where the effective address is stored in memory. Control fetches the instructions from memory and uses its address part to access the memory again to read the effective address. Few addressing modes require that the address field of the instructions be added to the content of a specific register in the CPU. The effective address in these modes is obtained from the following computation. So, the effective address, this is the equation we are having. Effective address is equal to address. Effective address is equal to address part of the instruction plus content of the CPU register. So, the CPU register is used in the computation, maybe program counter, an index register or a base register. We have a different addressing mode which is used for different applications. This is called the indirect addressing mode. Next, coming to relative address mode. So, it is the mode that the content of the program, it is in this mode the content of the program counter is added to the address part of the instruction in order to obtain the effective address. This is called relative addressing mode. Next, coming to indexed addressing mode. So, in this mode, the content of the index register is added to the address part of the instruction to obtain the effective address. And index register is a special CPU register that contains an index value. This is called index addressing mode. Next, coming to base register addressing mode. In this mode, the content of the base register is added to the address part of the instruction to obtain the effective address. This is similar to the indexed addressing mode except that the part of the register is now called a base register instead of an index register. So, we have some numerical example for this base register addressing mode. We have to show the difference between the various modes. We will show the effect of addressing modes on the instruction defined in the figure. So, I have a small figure here. So, this is the figure. So, if you see this, this is a numerical example. So, in this diagram, we having this is the 64, this is the addressing modes. So, it is a 2-word instruction. It is a 2-word instruction address. It is the 2-word instruction at address 200 to 200 and 201 is a load to accumulator. So, it is a two-word instruction. It is a two-word instruction. So, this is the diagram. So, it is a two-word instruction at address 200 and 201 is loaded the accumulator, instruction with the address field equal to 500, okay, equal to 500, and the first word of the instruction specifies the operation code and mode, and second word specifies the address part. So, the first word of the instruction specifies the operation code and mode, and second word specifies the address part. Okay. The PC in the PC has the value 200. Here if you see the diagram, in the PC we having the value 200 for fetching this instruction. If you have fetching for the instruction, the content of the processor register, R1 is 400. So, this is the R1. The content of the processor register R1 is 400, and the content of the index register XR is 100, and accumulator receives the operand after the instruction is executed. So, in the direct address mode, at the direct address mode, the effective address is address the part of the instruction 500. Instruction address is 500. So, at the direct address mode, the effective address is address part of the instruction is 500, and the operand to be loaded into the accumulator is 500. So, accumulator lo 500 anedi load ayindi. So, in the immediate mode, the second word of the instruction is taken as a operand rather than the address. So, 500 is loaded into the accumulator. In the indirect mode of the addressing, effective address is stored in the memory at the address 500. Therefore, the effective address is 800. The effective address is 800, and the operand is 300, Okay. And in the relative mode, the effective address is 500 plus 202 is equal to 702. Okay. And the operand is 325, So, the value in the PC after the fetching the phase and during the execution phase is 202. So, in the index mode, the effective effective address is XR plus 500 is equal to 100 plus 500, 600, okay, 600, and the operand is 900, okay, 600. This is the address and this is the memory. In the memory, the operand is 900. So, in the register mode, the operand is R1 and 400 and loaded into the accumulator. Okay. So, in the register indirect mode, the effective address is 400, it equals to the content of R1, and the operand loaded into the EAC is 700, okay, 700. And the auto increment mode is same as the register indirect mode, except that R1 is incremented to 401 after the execution of the instruction. So, the auto decrement mode decrements the R1 to 399 prior to the execution of the instruction. The operand loaded into the accumulator is now 450. Okay. So, in this table we having the effective address and the operand loaded in the accumulator AC for a 9 addressing modes. Okay. This is the table. Okay. Nine addressing modes. So, in this diagram. Okay. So, next coming to data transfer manipulation. So, what is mean by data transfer and manipulation? The most computer instructions can be classified into 3 categories: data transfer instruction, data manipulation instruction, program control instructions. So, first one is data transfer instruction. So, the data transfer instruction moves data from one place in the computer to another without changing the data content. So, the data transfer instructions moves the data from one place in the computer to another without changing the data content. The most common transfer between memory and the processor register, between processor register and input or output, and between the processor register themselves. So that can be listed of 8 data transfer instructions used in many computers. So this is the table whatever we are having. So this is the table we are having. So this is the typical data transfer instructions. So here I am loading the data. Here the load the instructions has been load. Load is nothing but we are loading the instructions has been used mostly to designate a transfer from memory to a processor register, usually an accumulator. So the storage is nothing but the store instruction designates a transfer from a processor register into memory. So next coming to move. What is the use of move? The move instruction has been used in the computer with multiple CPU register to designate a transfer from one register to another and place between CPU registers and memory or between two memory words. Exchange. What is mean by exchange? An exchange registers swap information between an exchange register swap information between two registers or registers and a memory word. So that is called the exchange. What is meant by input and output? So input and output instructions both to transfer the data among processor registers and input and output terminals. Next coming to push and pop. Push and pop instruction transfer the data between processor registers and the memory stack. So different computer uses different mnemonic symbols for differentiating the addressing modes. So for example, we are considering a load to accumulator. We are considering a load accumulator instruction when used with 8 different addressing modes. In this having the this is the 8 addressing actual transfer in cases. Okay. So this is the direct address. Okay, direct address. So in this ADR address, direct address stands for an address. So ADR stands for, in the shortcut ADR we are having, it is called ADR stands for address. MBA, NBR. NBR is nothing but MBA is a number or a operand. X is an index register. So at the rate is symbol is called, it is a character, at the rate symbol character symbolizes an indirect addressing mode. At the rate is the indirect addressing mode. Dollar character before an address makes the address relative to program, to program counter PC, and hash character precedes the operand in an immediate mode instructions. So these are the different operations we are performed in the addressing modes. So these are 8 addressing modes. Okay. Next coming to data manipulation instruction. What is meant by data manipulation instruction? So the data manipulation instruction performs operations on data and provide the computational capabilities for the computer. The data manipulation instruction in the typical computer are usually divided into 3 basic types. One is arithmetic instruction, logical and bit manipulation instruction, shift instructions. These are the 3 types available in the data manipulation instructions. First one is arithmetic instruction. What is meant by arithmetic instruction? Arithmetic instruction is nothing but we are having the 4 basic arithmetic operations are called addition, subtraction, multiplication and division. Most computers provides instructions from all 4 operations. Some small computers have only additions and possibly subtraction instructions, and the multiplication and the division must then be generated by means of software subroutines. So that can be listed in the listed a typical arithmetic instructions in the table. So this is the table of the arithmetic instruction. Here we are having the increment. The increment instruction adds 1 to the value stored in the register or a memory word. That is called by increment. A number with all ones when incremented, that produces a number with all zeros. The decremented instruction subtracts 1 from the value stored in the register or a memory word. The number with all zeros when decremented produces number with all ones. So the add, subtract, multiply and divide instructions may be use different types of data. The data type assumed to be in processor register during the register execution of this arithmetic operation is defined by an operation code. An arithmetic instruction may specify fixed point or floating point data, binary or decimal data, single precision and or double precision data. The mnemonics for the 3 add instructions that specifies the different data, that specifies the mnemonics for the 3 add instruction that specifies different data types as in below. So add I, add 2 binary integer numbers. Add I means adding 2 binary integer numbers. Add F, add 2 floating point numbers. Add F means we are adding 2 floating point numbers. Add D, add 2 decimal numbers in BCD. Binary coded designation. Okay. So ADD means add D means add 2 decimal numbers in the BCD. So these are called the arithmetic instructions we are following in the table. So next coming to logic and bit manipulation instruction. So logic and bit manipulation execution is nothing but logic instructions perform. The logic instructions perform binary operations on strings of bits, bit storage registers. They are useful for manipulating individual bits or a group of represent binary coded information. The logical instruction considers each bit of the operand separately and treat it as a Boolean variable. Okay, Boolean variable. So by a proper application of the logical instruction, it is possible to change the bit values to clear a group of bits or to insert a new bit values into the operand stored in the register memory words. Some typical logical and bit manipulation instructions are listed here. So I have in the table, this is the table. Here we have the clear operation. So this is the logic and bit manipulation instructions. Clear. The clear instruction causes the specified operand to be replaced by zeros. Clear is nothing but you are clearing the instruction. Clear the instruction causes the specified operand to be replaced as a 0. The complement instruction produces the ones complement by inverting all the bits of the operand. The AND, OR and XOR instruction produces the corresponding logical operations on individual bits of the operands. The logical instruction can also be used for performing bit manipulation operations. There are 3 bit manipulation operations possible. A selected bit can be cleared to 0 or can be set to 1 or can be complemented. Okay, and can be complicated. The AND instruction is used to clear a bit or selected group of bits of an operand. OR instruction is used to set a bit or a selected group of bits of an operand. Similarly, XOR instruction is used to selectively complement bits of an operand. So these are the 3 things we are 3 bit manipulations operations we are having possible. So next coming to shift instruction. So shifts are operations in which the bits of a word are moved to left to right. Shifting is nothing but we are moving the bits from left to right. The bit shifted it at end of the word determines the type of the shift used. Shift instructions may be specify logical shift, arithmetic shift or rotate type operations. In either cases, the shift may be to the right or the left. So I am having the table. In this table, we are having the logical shift right. Logical shift right insert to the end bit position. End position is the leftmost bit position for shift right, the rightmost bit position for the shift left. The arithmetic shift usually confirm the rules for signed 2's complement numbers. The arithmetic shift right instructions must preserve the sign bit in the leftmost position. In sign bit is shifted to the right together with the rest of the numbers, but the sign bit itself remains unchanged. So, this is the shift right operation with the end bit remaining the same. The arithmetic shift instruction insert 0 to the end position and is identical to the logical shift instructions. Okay. So, this is the table of the shift instruction. Okay. Next, program control. So, what is meant by program control? In program control instruction specifies the conditions for altering the content of the program counter. We are changing the value of the program counter as a result of the execution of a program control instruction causes a break in the sequence of the instruction execution. So, the instruction provides the control over the flow of the program execution and capability for branching to different program segments. We are having some program control instruction that can be listed in the table. So, this is the program control instruction. Branch and jump instructions may be conditioned and unconditioned. An unconditioned branch instruction causes a branch to the specified address without any condition. The conditional branch instruction specifies a condition such as branch is positive or branch is 0. The skip instruction does not. The skip instruction does not need an address field and is therefore 0 address instruction. A conditional skip instruction will skip the next instruction if condition is met. This is accomplished by incrementing the program counter. The call or return instructions are used in conjunction with subroutines. We are comparing the instructions forms a subtraction between two operands, but the result of the operation not retained. However, the certain status bit conditions are set as a result of the operation. Similarly, the test instruction performs the logical AND of two operands and updates certain status bits without retaining the result or changing the operands. So, this is the table of the control instructions. Okay. Next, status bit conditions. All ALU circuit in the CPU have status register for storing the status bit conditions. Status bit conditions are also called condition code bit or flag bit. Okay. So, having the block diagram of the 8-bit ALU with 4-bit status register. So, this is the diagram. Okay. So, in this we are having the 4 status bit, 1, 2, 3, 4. 4 status bits are symbolized as C, S, Z and V. The bits are set or cleared as a result of an operation performed in the ALU. So, the bit C is a carry is set to a 1, is set to 1. If the end of the carry C8, end of the carry is C8, okay, is set as 1. If it is cleared to 0, if carry is 0, if it is clear to 0, then carry is 0. If S sign is set to 1, its highest order bit F7, this is the F7 is 1, it is set to 0 if it bit is also 0. So, bit Z is 0 is set to 1 if output of ALU contains all zeros, it is clear to 0, otherwise, in other words, Z is equal to 1 if the output is 0 and 0 is equal Z is equal to 0 if all the output is not 0. Bit V overflow is set to 1 if exclusive of the last 2 carries equal to 1 and clear to 0, otherwise the above status bits are used in conditional jump and branch instructions. So, this is the working of the status register bits. Next, subroutine call and return. So, a subroutine is a self-contained sequence of the instructions instructions that performs a given computation task. The most common names used are call routines, jump to subroutines, branch to subroutines, are branch and save return address. So, a subroutine is executed by perform the two operations. First operation is the address of the next instruction available in the program counter is stored in the temporary location, so the subroutine knows where to return. Second one is control is transformed to beginning of the subroutine. So, these are the two conditions we are following, operations we are using in the subroutine. So, the last instructions of every subroutine commonly called return from subroutine transfer the return address from the temporary location in the program counter. Different computers use a different temporary locations for storing a return address. The advantage of using the stack for the return address is that when succession of the subroutine is called, sequential return address can be pushed into the stack. So, this is the SP, okay. This is the stack pointer, and I am going to decrement the stack pointer SP minus 1, and we are going to push the content of the PC onto the stack, and PC is the effective address. We are transferring the control to the subroutine. Okay. Instructions that returns from the lost subroutine is implemented by the micro operations. So, this is the PC here. This is PC is a program counter. We are popping the stack and transfer to program counter, and after that stack pointer is incremented. So, this is the two conditions we are having. Next, program interrupt. Program interpreter refers to the transfer of program control from a currently running program to another service program as a result of an external or internal generated request. So, the interrupt procedure is similar to the subroutine call except for three variations. First variation is the interrupt is initialized by an internal or external signal. So, the address of the interrupt service program is determined by the hardware, and interrupt procedure usually stores all the information rather than storing only PC content. Okay. So, this is called the program interrupt. Types of interprets. There are three major types of interprets that causes a break in normal execution of the program. They can be classified external interrupts. So, these come from input output devices, from a timing device, from a circuit monitoring the power supply, or from any other external sources. Example, input output devices requesting the transfer of data, input output devices finished the transfer of data, elapsed time of an event or a power failure. So, this is called the external interprets. Next, coming to internal interrupts. These are arises from illegal or erroneous use an instruction or data. Internal interrupts are also called as traps. For example, interrupts caused by internal error conditions or register overflow, attempt to divide by 0, and invalid operation code, stack overflow, and protection violation. Internal and external interrupts are initialized from signals that occur in hardware of CPU. Next is software interrupts. A software interrupt is initialized by executing an instruction. Software interrupt is a special call instruction that behaves like an interrupt rather than subroutine call. So, these are the three interrupts we are having. Next, coming to last one, execution of the complete instruction. So, the control unit must be capable of taking the input about the instruction and generates all the control signals necessary for executing that instructions. For example, we are writing a signal for each state element, the selector control signals for each multiplexer, the ALU's control signals, etc. In this below, we are showing the complete data path implementation of the MPI's architecture along with an indication of various control signals required. Okay. In this execution of a complete instruction, we are adding the R3, R1, fetching the instruction. After fetching the first operand, the content of the memory location is pointed by the R3. We are performing addition, and after we are loading the result in the R1. So, these are the working of execution of the complete instruction. So thank you.